everyone. In this video, I am going to discuss about one of the most commonly used asymptotic notation, the big O notation. So you are already familiar with this one since we discussed this last time, and this describes the worst case na bound for an algorithm's running time. Okay, so assuming that we have some function f of n, wherein f of n is the running time of a certain algorithm, and after some input n sub 0, we have another function g of n multiplied to some constant c that grows at least as fast as the f of n. Okay, so as you can see, the running time for the cg of n is much bigger compared to that of f of n. Okay, so the f of n will be less than or equal to the function cg of n for all of the inputs that are greater than or equal to n sub 0. So why is this the case? So pwedeng in this area or in these input sizes, it is possible that your f of n could could grow larger than cg of n, but after some value n naught, or after some input size n naught, then the f of n will always be less than or equal to some cg of n. Okay, wherein the constant c is equal to 0 and the n naught is equal to n naught will be greater than or equal to 1. So this big O notation, this represents the upper bound of an algorithm's time or complexity. So essentially, this provides some upper limit, provides an upper limit on how an algorithm's running time scales as the input size increases. Do you remember in the previous video about the definition of asymptotic analysis? So we mentioned, right, that it's a way to understand the algorithm's behavior as the input size approaches infinity. Okay, so if this is the case, if the f of n, if this function f of n is indeed less than or equal to this function cg of n after some n naught, then we can then say that this function f of n is being bounded or contained in O of g of n. Okay, so yeah, right. Okay, so let's have a little bit of an example. So assuming that we have this function f of n, and then this f of n is equal to 3n plus 2. And then we also have another g of n, which is equal to n. So can we prove that this function f of n is being bounded by O of g of n? Okay, now the f of n is less than or equal to cg of n, as we have stated in there. And then, so we just replace f of n with the value of 3n plus 2 and less than or equal to cg of n. Now, how do we actually prove this one? So what we want to do is to look for some constant c. Okay, so assuming that the constant value is 5. Okay, so essentially, what we do is just replace the c with 5, and then the n is equal to g of n is equal to n, right? So this is 5n. Now, how did we get the 5? So one very easy way to do it is to like add the coefficients here. So for example, 3 plus 2, that will give you 5n. So then this will be, if we replace the n with 1, let's say, so this will be 3 times 1 plus 2, which is equal to 5. And then on the right side, 5 times 1, that will also be equal to 5. So that is 5 less than or equal to 5. So we can then say that the function n, f of n, 3n plus 2, is being bounded by O of n by the function g of n, given that the constant c is equal to 5 and the n naught is equal to greater than or equal to 1. So one way to understand that is that after some input n naught which is equal to 1, or initial or some input size 1, then with the constant value of 5, so this 3n plus 2, f of n equals to 3n plus 2, will always be contained in the function 5n. Okay? So meaning after some input size 1, so 5n will always be bigger or will grow as fast as 3n plus 2. Okay? So, well, we can also say that 3n plus 2 can be bounded by n squared or n cubed, because technically the 3n plus 2 is linear, right? And n squared, or let's say n cubed, will be larger than linear. But what we want is the asymptotically type na function, which is O of n. Okay? Now, this is the more formal definition of the big O notation. So we have two functions, f and g, and they are non-negative na functions having non-negative na arguments. So O of g is that we have a function such that function is a non-negative na function such that for every constant c and n naught, they are all greater than 0. Again, saan nanggaling si n naught? Si n naught is the, as you can see here, after some input n naught. Okay, and then the cg of n is, the c is some constant value that we multiply to g of n. Okay, so f such that f is a non-negative function such that for every constant c and n naught greater than 0, f of n is less than or equal to c g of n for all n that follows after this input size n naught. Okay, so yeah, so g of n, then we can say that the function g of n is an asymptotic na upper bound to f of n. And using the big O na notation, our asymptotic na upper bound, or yung g of n, which as you can see here, this function cg of n will act like an upper limit to our function f of n, or an upper bound. Okay, so using the O notation, we can then often describe the running time of an algorithm merely by inspecting the algorithm's na overall na structure. So for example, if we have in our pseudocode and we are using a double loop, then this will have a big O of n squared. Okay, and just by looking at the pseudocode, we can already tell the speed of a certain algorithm as the input size is growing. Okay, so since the O notation describes the upper bound, when we use it as bound of the blank running time of the algorithm, we have a bound on the running time of the algorithm on every input. So what is the answer in here on the blank? Describes the upper bound when we use it as bound of the what? Of the worst case na running time of a certain algorithm. Okay, so I guess we can now move on to big omega notation. So what is the big omega notation? Okay, so let us see first a graph. So assuming that we have a certain function f of n, and then after some input size n naught, we can see that we have this function cg of n, which is being bounded by a function f of n. So, nag-ano naman sila, nag-reverse na siya. So, kung sa big O kanina, the f of n is less than or equal to Cg of n. But in the big omega notation, the function f of n is greater than or equal to Cg of n for all inputs that are greater than or equal to this input size and not. So why is this the case? So for example, before the n naught, we can see that the f of n even performs better compared to g of n. But after some input size n naught, then we can already see how f of n grows as much as fast as cg of n. Okay, so we can then say that um, this uh, this function f of n is bound is being is containing this function cg of n. Okay, and well, this f of n could be greater than or equal to cg of n, as you can see in the graph. Nasa taas na yung f of n. Okay, yan lang yung tatandaan nyo. For all input sizes that are greater than some input size and not for given that the constant value c multiplied to g of n is greater than 0 and the n naught is greater than or equal to 1. Kasi we don't, why is this greater than or equal to 1? Because we don't have an input size which is 0 or negative. Okay? Now, so let's have this example. So we have this f of n equals 3n plus 2, and then g of n, which is equal to n. So can we prove that f of n is contained by the omega of g of n? Okay, omega of g of n. So what do we mean by that? So sinasabi lang natin na yung f of n will act like will be bounded by Cg of n, but in this case, lower bound siya. Okay? Yung sa big O naman, bounded si f of n ng Cg of n, pero upper bound yun siya. But in the omega na notation, what we are looking for is some function Cg of n that will act like a lower bound to f of n. Okay? So, can we prove that f of n is being bounded by the omega of g of n? So f of n then is greater than or equal to cg of n. So we replace f of n and cg of n. So 3n plus 2 for f of n, and the g of n, as we know, is n, right? And our job is to look for the constant value c such that this assumption will be true. This f of n greater than or equal cg of n will be true. So assuming that we use a constant value of 1, okay? And then we replace g of n with n. So now we have 3n plus 2 and it is greater than or equal to n. Okay, so when can this be true? When can this be true? So now we have to look for that certain value and not. And if let's say we replace n with a value of 1, so that will be 3 times 1 plus 2, and then that will be 5, and then greater than or equal to n equals 1. So now that is true, right? Correct na siya. Kasi we have proven that indeed with this constant value equals 1 and n naught greater than or equal to 1, then we can then say that this 3n plus 2, f of n 3n plus 2 is being bounded by n. Okay? So, kung kanina, balikan natin. Yung sa big O. Sa big O notation, balikan nga natin siya. Yung sa big O, yung f of n is being bounded by cg of n. Tapos, upper bound ito siya. So, this has a value of 5n. So, this 5n will always be bigger or grow at least as fast as 3n plus 2 after some input and not, which is 1. Pero sa omega naman, big omega notation, yung hinahanap natin ay yung CG of n, which will act as a lower bound to f of n. Okay? And after some input size and not. At nahanap natin yun by using a constant equals 1. So we can then say na itong 3n plus 2 will always be bounded by n. So 3n plus 2 will always be greater than this n after some input and not, which is equal to 1. Okay? So let's have another example. So f of n is equal to 3n plus 2 again. So our f of n here is equal to 3n plus 2. And the g of n, so here, is equal to n squared. Now, can we say that this f of n is being bounded by g of n? Can we say that this g of n is a lower bound to f of n? So let us try to prove it. So f of n is greater than or equal to cg of n, since this is the omega. And then, and we are looking for the lower bound cg of n. So we have 3n plus 2 is greater than or equal to c of n squared, since our g of n is n squared. And now, can we possibly find any constant c that will make this true? That will make this statement true? No, it's not possible. Any value of n, regardless of the value of n, the n squared will always be bigger compared to 3n plus 2. Okay, so we can then say that the f of n is not being lower bounded by omega of n squared. So hindi pwede na itong cg of n en squared kasi hindi to. Kasi so mas lalaki to siya. Mas lalaki yung running time niya compared to f of n's na running time. Okay, so kung babalikan natin yung example natin dito kanina. What if yung g of n is equal to log n? Can we say that this function f of n 3n plus 2 will be bigger than log n at some point? The answer is yes, because linear is bigger than log n. Okay? But what we want is the asymptotically tight na lower bound, but not the one that the log n, okay, which is not asymptotically bound. Okay, so do you understand now? Okay, let's move on. So more formal na definition. The f of g is the set of non-negative functions with non-negative na arguments. And the big omega of g states that f such that f is a non-negative na function such that for every constant c and n naught greater than 0, such that function g of n multiplied to some constant c is always less than or equal to f of n for input sizes greater than or equal to initial input and not. Okay? So, ibig sabihin lang nito, meron tayong function cg of n which will always be lower, which will grow which will not be larger than the function f of n after some input and not. Okay? So, if the big O notation provides the asymptotic na upper bound, yung big omega notation naman, this will provide the asymptotic na lower bound. But we will not be dealing with this lower bound notation or the big omega notation as much as the big O notation. Can you guess why? Can you guess why again? Because these omega notation, this will be describing the best case. And often, to get the best case, the inputs are trivial or it's meaningless when we use it for analyzing the algorithm. But we want to always consider the worst case, and we do that by using the big O notation. Okay, and now what about for the theta notation? So theta notation is also what we call as the asymptotically tight bound, and this is used to describe the average cases. So assuming that we have a function f of n, so we will have a function c2 g of n that will be greater than or equal to f of n, and then we also have function g of n with a constant c1, which will grow not larger than f of n. Okay, so after some input size and not. As you can see, you can think of the f of n like being sandwiched in between this c2 g of n and then c1 g of n. So in the big O and then in the big omega, what we did was we looked for some constant c. But in the average case, and as you can see, this function f of n is being sandwiched in between two functions. We are going to look for two constants, c sub 1 and then c sub 2. Okay, so we can then say that in the theta notation, the function f of n is greater than or equal to c1 g of n, which will act like some lower bound, and then the c2 g of n then will be greater than or equal to f of n, wherein both of the constants c1 and then the c2 will be greater than 0 for all input sizes going to infinity after some input and not. Okay, so now let's have a bit of an example. So we have f of n is equal to 3n plus 2, and then g of n is equal to n. So we want to prove that f of n is in O of g of n. And then, no, we are supposed to be using theta here, not the big O. Okay, so, and to do that, we'll have to look for two functions. So f of n should be less than or equal to cg of n, and f of n is greater than or equal to cg of n. And we can do that by looking for some function, for some constant c for this part. Now, one possible is 5. So by like adding all the constants here. And when is this true? For what? When is this true? For what value of n naught? And this will be true if n is equal to 1. And even if we replace it with 2 or 3 and 4, this will always be true. So what about for this one? The f of n should be greater than or equal to cg of n. Now, 3n plus 2 is greater than or equal to cg of n, wherein cg of n is n, by using the constant 1. Okay? And if we replace this with, let's say, 1, and naught is greater than or equal to 1, so 5 is greater than or equal to 1, and this will always be true for n naught greater than or equal to 1. Okay, so we can then say that 3n plus 2 is being sandwiched in between these two functions, n and then 5n. Okay, now for this example, you can explore it. So for instance, if we have this f1 of n equals 10n cubed plus 5n squared plus 17. So we want to look for its average for its theta asymptotic notation. So now f sub 1 n is greater than or equal to some 10n cubed and less than or equal to 10 plus 5 plus 17n cubed. So where did we get this? So first is we just took this coefficient, which is 10 of n cubed. And then for the upper bound, on the other hand, we just summed up all the coefficients, 10 plus 5 plus 17. So then we have some constant 1, which is 10, and then some constant 2, which is 32. And this will be true for all cases, for all n greater than or equal to 1. Okay? So now, this formal definition of the theta, f of g non-negative functions of non-negative na arguments. So f such that f is a non-negative function such that for every constant c sub 1 and c sub 2, as well as the input size greater than or equal to 0, the f of n will be greater than or equal to c sub 1 times g of n and less than or equal to c sub 2 g of n for all inputs greater than or equal to n naught. Okay? So again, as I mentioned, we can then say that this function f of n is being sandwiched between these two functions, this function g of n with two differing constants c1 and c2. Okay, so the theta notation is used to describe the average na cases. And also take note that in some resources, you can see that instead of using the symbol, they are using the symbol instead. F equals theta of G. So they are essentially the same. Okay. Now, for a brief summary, so these are three most common na asymptotic na notations. So we have the big O of G versus the big omega of G versus the theta of G. Okay, so what are the difference between the three? So for the big O, so the f of n is less than or equal to c2 of g of n. So this g of n will act like an upper bound to the f of n. But for the big omega, the c1 g of n will be less than or equal to f of n. So the f of this g of n then will act like a lower bound to your f of n. So the f of n's graph will always be above g of n after some input n, above or equal. Okay. But for the theta, so the f of n is being sandwiched in between c sub 1 times g of n and c sub 2 g of n. Okay, so now a little quiz. For the big O, this describes the upper bound or the worst case. But the big omega of g, this describes the lower bound for the best case. But for the theta, this describes the average na cases. And more summary, in the big O, so the F is no larger than G. So F will always be lesser than G. But for the big omega, then F will be greater than or equal to G. F will always be, so since we are looking for the lower bound here. But for the theta, so F is nearly similar to G. Okay, so this, and in practice, we always use the big O notation, but in general cases, the average. Okay. So, what to use? Average case versus the worst case. So, as we know, an algorithm may run faster on certain data sets than on the others. Since we have discussed that the structure of the input also affects the running time. So we will try to find the average case, but it can be very difficult. So that's why we typically use the worst case complexity, which can be measured using the big O notation. Okay, So for example, in certain applications like traffic control or surgery, what we are interested in is the worst case time complexity because this is of very crucial na importance. Okay? Yeah. Yes, that's all for today. Thank you for listening.